Good afternoon, and welcome to NovaTech's IEC 61131 Introduction. My name is John Popiak, and I'll be your presenter today. There's quite a bit of information to cover in this 45-minute brief introduction to 61131-3, and what we will go through is a review of the seminar agenda, where each of the 5 math and logic toolkits within the IEC 61131 umbrella will be discussed, which includes ladder logic, structured text, function block diagram, sequential function chart, and instruction list. A daunting task is to determine where each of the toolkits, if and when they should be used. That will be reviewed under the applications, which will be run real time. We'll also show you how to write custom user-defined function blocks for repetitive tasks and execution within the OrionLX. And each one of the IEC examples will be online, so you can see the interaction between the programming environment and the online status. The demonstration is built upon a specific architecture, which has been shown in this slide. The NCD configuration PC, which this webinar is being broadcast from, shows the programming environment. The central archive appliance would be the OrionLX. There are 3 serial port connections and 2 Ethernet port connections, as illustrated in this diagram. The Orion has been configured as a master, speaking both DNP and DNP Ethernet to the various DNP-capable devices. Also, the Orion is speaking proprietary protocol for specific manufacturers' IED implementations, such as the attachment serially to port 1 device, which is a typical overcurrent relay found in a distribution or transmission substation. Serial port 2 and serial port 3 are the attachments illustrating the gathering of data from the Orion, by the OrionLX from the DCIO. This NovaTech DCIO reads in discrete inputs, is able to control discrete outputs, and can read milliamp and millivolt signals, transducing them into a numerical quantity able to be executed by a microprocessor or the IEC logic. Serial port number 3 is connected to a Biotronics 70 series meter, reading metering quantities as well as discrete inputs and controlling discrete outputs as the meter is configured. For those of you familiar with the IEC environment, we will be taking the IEC 1131-3 application and obtaining tags from the Orion database. Each one of the IEDs has been pre-configured under the Ports, Devices, Inputs, Outputs, and Pull Groups tab within the NCD programming environment or configuration environment. The scan rates, as shown here, are varying in that the Orion will poll for these data elements, which were configured in the IEC or within the NCD program, and populate the database within the Orion, allowing every application, whether it's a protocol, a logic package, or an archive package, to update the database accordingly. The scan times are very critical in that it determines the responsiveness of the other applications as well as logic to perform their requisite actions. Additionally, within this application, there is a screen which we have created from the NovaTech application -57, part of our previous webinar on XML, which will be utilized to show the update of the logic and the interaction of the various inputs and outputs with the logic we have programmed. A little behind-the-scenes explanation should suffice with the interaction between the OrionLX database and the IEC logic. The Orion architecture is such that each of the protocols from the IEDs on the left-hand side of the screen are updating the various tags used within any application. In this instance, the tags could be a physical discrete input, such as that from a 52A, 52B contact, a metering quantity, such as per phase amps, volts, VARs, the center cylinder, and the arrows, the blue arrows beneath the central reddish cylinder, show that there is an update between the configured NCD applications for each of the protocols, whether DNP or manufacturer specific. The cylinder on the right-hand side illustrates the programming environment for the IEC languages, which include instruction list, structured text, function block diagram, sequential function chart, and ladder diagram. On this slide, within the parentheses, are the similarities to some of the common languages which you may have encountered in other environments, such as assembly language, graph set, ladder logic from a programmable logic controller, or other visual or structured text languages. The arrows beneath the cylinder on the right-hand side also show the update of the various tags which are passed between the IEC 61131-3 language and the Orion database. These are virtual inputs and outputs. The virtual inputs and outputs, as well as the real IED inputs and outputs, are accessible to all the IEDs and applications, and they are bridged by the Orion database. It's important to note that both of these update tasks between the IEC and the IEDs are asynchronous, so the responsiveness is appropriate to the scan rates selected. Perhaps it would be advisable to review the NCD programming environment. Within NCD, if one would configure, you would go down into the logic drop-down menu once you have configured your serial ports and your Ethernet ports. Within the communications, we can see that through the text interface with the Orion, we have each one of the IEDs polling, and by the quantity of polls, you can see each port is polling at a dissimilar rate. Within the programming environment, on the left-hand side of the screen, we have the ability to create a new program, and the programs which we create would appear in this drop-down tree. We have many programs pre-programmed, and the instructions for each one of the programming examples would be available through this pick list, which shows each of the various instructions which can be placed from the pick list to the programming environment. We are in the offline mode, so each one of the various tags are being updated real time according to the poll rate of the program. On the bottom of the screen, we have the tags which are included in this application. These are the tags which are updated under the Inputs and the Outputs tab from the IEDs which are attached. We can see that from the filter options, all of the ports are visible, and we can perform a filter on the points which are available from the total Orion database to the database on the right-hand pane, which are the tags which we would be utilizing in our logic. The pick list would allow us to drag from the left-hand side of the screen and select any one of the arrows, right or left, to drag the point from the left-hand pane to the center pane. Within the typical application for common logic task review, we have a central Orion communicating to each one of the IEDs. The lines in the right-hand upper corner illustrate a connection, whether it is a serial connection or an Ethernet connection, and each connection the master Orion application will generate a communication fail tag, and it will update the status depending upon whether that port or application can communicate to the attached IED. Traditionally, we perform this aggregation of data utilizing -35 Logic Pack, -83 Math and Logic, or -99 Advanced Math and Logic. Within our webinar, we shall illustrate the various languages, capability, and methodology to perform the global bit generation as we would have done in our traditional Orion logic packages. So each one of the IEDs, if it does not communicate, will create a bit status for COM fail, and we're aggregating all of the COM fail paths and creating a general bit to be sent to SCADA, which would be a general COM fail. Back to the programming environment. Instruction list programming is similar to that which one would see if they had used an old microprocessor, such as a Z80, or perhaps a Hewlett-Packard calculator with reverse Polish notation, where one would load a constant into an accumulator, then type in a value and a function for which one would execute an instruction. Once the instruction is executed, the resultant value would be placed in the accumulator. Within the instruction list, we would go from, again, write our program from the available functions in our programming environment. We would create a programming area to begin the instruction list program. We could then insert comments in green and add the instructions. Each one of the various COM fail bits has been added from the filter options, where we see all ports. We've listed all tags alphabetically, and we will see that our COM fail appears from the left-hand side of the list, and we have drugged the COM fail to the right-hand side of the list, showing that each one of these tags are available in our logic package. If we can simulate this program offline, but we shall not do that for the sake of this webinar, given our limited time, and the fact that if we go into the simulate environment, we would have to rebuild the program, reload the program to the Orion, and then restart the Orion. That would take up a bit of time, so we will go online with our program. Our program has been built, it's been downloaded, and we will attach to the Orion. For those of you utilizing packages previous, such as the -99 Advanced Math and Logic package or the -83 Math and Logic package, the online monitoring and execution of the programs was not possible. IEC gives you this definite advantage as opposed to the other options. I will continue online, and we'll see on the right-hand side of the run bar, or the status bar, there is a run indication indicating that each one of the instructions are being executed. The execution rate we've set for 500 milliseconds, and on the right-hand side, if we would highlight each one of the logic package instruction, or the logic packages, we would see that there's a cycle management grayed out selection. And that selection, if we were offline, would allow us to stage the execution of each package, as well as the frequency and periodicity of the execution of each package. On the right-hand side, that we're online, there is an indication of whether the variable for the COM fail is true or false. If I would unplug my IED, for example, the IED would take time to stop communicating, and it would indicate that there is a communication failure. For example, my overcurrent relay, I have unplugged the communication cable from the serial connection, and you can see that the cell 501 relay COM fail has stopped communicating because the cable is unplugged. The instruction list gives us an indication, but of course we can perform this in other languages, such as in structured text. For those of you who have utilized the -IEC application, or the Advanced Math and Logic application, you would see that the instructions are similar to the Advanced Math and Logic or the Math and Logic application. Here we have a comment. We're creating a global COM fail bit in Logic. We're taking each one of the tags, which would be selected from the drop-down menu. We have included each one of the tags that we've seen before, and our variable, which would be sent to Logic, we had created. Each one of the tags for each one of the languages, I've created a COM fail instruction list, ladder diagram, structured text, and function block diagram. The Logic and structured text, creating a different IEC COM fail, would be that I've created a Boolean variable. The Boolean variable is predicated upon any one of the COM fail variables, which I selected from my input database of the Orion. I've created my virtual output, or my virtual input tag, and you can see that each one of my values is true. If I would plug back the cable to my protective relay, and when communications would start, again, one would see that when the device did come online, the IEC value for all of the languages would then come online as a true value. I've done the same in ladder diagram. I've created a COM fail. I've taken each one of my contacts from the right-hand side, or the left-hand side of my screen, and I have taken and attached each one of the variables to a normally open and normally closed contact, which shows me perhaps more visually than in the instruction list or the structured text example that my COM fail has occurred with the cell 501 relay. I can drag and drop the tags to show much more of a visual indication that my communications has failed in this IED. Moving over to function block diagram, for those of you who are more familiar and would like block programming rather than icon-based programming, what we have done is we've taken each one of the blocks from the OR column, which would be in the instructions, and I could pick from my Boolean logic the OR instruction, and I've taken each one of the COM fail bits. Perhaps I can highlight this a little bit and improve the view, that with each one of these tags I can see and force the value of the tag. My virtual inputs do show that the COM fail for each one of the tags is now at a value of false for the Brytronics meter and the DCIO, and still failed for the overcurrent relay. Each one of the tag attributes within the IEC programming environment allows access to every attribute of the tag. The value, the online status, how many changes that tag has undertaken, any tag text which has been included for display on a web page, the date of change, and the time. The IEC logic does allow the access of each one of these pieces of information. So far we have reviewed the ability to perform and create a virtual input which would appear in the programming list for each of the IEDs. It's a relatively rudimentary function. Perhaps we should go to the next application. The next application is current averaging. From our protection capability, we could read per phase current, but in this application we'll be reading from a measurement device, a Biotronics 70 series meter. This application will take from the meter 3 phases of current. It will add them together and divide them by 3. In this case, so that the result can mirror advanced math and logic and math and logic, the -9983 application. We'll mirror this application in structured text since it most clearly matches the previous methodologies within the OrionLX. Back to our programming environment online, you can see that the tree has blocks indicating the types of programs which we have created. To create a new program, we would go into Create New Program, and it would give us the luxury of selecting one of the various languages. If you have selected a language and would wish to convert it to another language, the IEC logic does allow that within the NCD configuration and programming environment. Within this application, I've created a program called iAverage. In this application, I go to my variable screen. I will be taking each one of my currents, phase A, phase B, and phase C, and I will be converting them to a long integer. IEC 1131-3 logic is very particular with keeping variable types the same. So in many cases, so I don't have overflows of my mathematics, I may wish to keep the mathematics and convert them into a long integer format or a long format so that I don't have any errors in my runtime that logic results are too large for the variable type I've selected. So from the meter, what I've done is I have first taken from my serial port the amps phase A, B, and C from my Biotronics meter. Real-time execution, I can see they're giving me a value of approximately 260 to 270. What I've done is, within my logic, I have taken and created a variable stuff. My stuff variable is a long integer in that, keeping the addition of all my other long integers the same, my container or my variable, which is not visible to any of the applications since I have not written it to the Orion database, I am able to add all of the per phase measurements, divide by 3, and then transfer that variable, stuff, convert it to an integer, and I've created a variable called IEC I 3-phase average, which was created in the Virtual Inputs tab. IEC 3-phase average, my minimum and maximum value has been selected, and I could also see the value being 260. This is an internal value, which is a scaled value. It's not primary units or secondary units. For those of you who have utilized the IEC or the Biotronics meter, you know that scaling will have to occur. So one of the other tasks which may be of use would be an unscale function. If you are using, as in this case, a Biotronics meter, reading up the scaled functions of per phase current, volt, watts, bars, or frequency, and having the logic application perform the unscale application to perform or view and visualize the elements in the application being in primary units. So, based upon this, I've created a program called in function block diagram, which would be current unscale. Let's go to the application programming environment under function block diagram, which is Bytronics meter VAN the primary. The programming environment has allowed me to read my scale and unscale functions directly from the DNP memory map. And these functions, or these variables, will reflect any changes in the CT ratio per phase. So in case the user changes the CT ratio real time, the unscaled value will be properly converted. I've created a comment in my function block diagram which illustrates the equation I'm utilizing in order to convert the unscaled value to a scaled primary value. I'm taking my scale factor, dividing it, converting it to real, multiplying it by the equation's conversion factors, and I'm reading the real-time value, which in this case is 25,821. I can force those elements on time, real time, to test my logic, but I'm reading them real time. I am dividing them by a constant of 32,767, and I'm coming up with a number 118.225 for my voltage. I also have created within this routine a get point instruction that in case the meter is not communicating, I can affix an online attribute which would alert SCADA that this derived value, or this unscaled primary value, is either being updated online or offline, that communications have ceased. Thus, within this application, I go to my variable list. I've created various internal variable structures to save my online status and affix them to my derived value. I've also taken my voltage, my current and my scaling factors and included them as tags for each one of the variables that I've included in my divisor instruction and my multiply instruction. I've had to convert each one of my variables to a real number so that whenever I go to my web page, I have meter quantities. In this case, only phase A current is updating. I have logic, which will update the other quantities. Usually, scaling of various IEDs or unscaling is a repetitive task. It would be very convenient to create a user-derived function block which would, again, make these repetitive tasks much easier to program. We will create a voltage unscale block to create unscaled quantities to primary units and display them on our web page. We'll use function block diagram to create a user-derived function block. Let's investigate the programming environment. I have a Bytronics voltage unscale block, which you can see by the icon on the left-hand side of the screen, and FB is a derived function block. We've copied the logic from our previous function block into a voltage derived function block. Within the derived function block, we've created variables. The variables are given a name, a type, an attribute, and we can initialize the values of each one of the variables. Whenever the derived function block would be visualized in other languages, we would see a graphical square with variables on the left-hand side of the block and the right-hand side of the block, and that is where the user or the programmer would attach the variables, and this instance of the subroutine would be replicated in the compiled logic repetitively for each usage of the instruction. I've created a user-derived function block for voltage, current, power per phase, and power for 3-phase, where the output of the block gives me my unscaled power, or voltage in this case, and we also have the ability to attach an online or offline status to it. Perhaps we should go into the usage of the ladder diagram. Since we've created this user-derived function block to be used in other languages, let's illustrate a typical logic construct utilized in many relaying diagrams for ladder diagram. I'll select FBD usage program, and for each one of my user function blocks, I have created an unscaling block that on my simulator, if I energize input number 7, you will see that the tag is true. And each one of my quantities, I'm bringing in my scale factor from my meter, I'm bringing in my quantity measured, and I'm also in another value, a tag name. And each one of the various attributes are visible. I can click on the usage, and I can see a real-time update of every one of the quantities for the execution of this diagram. The output, I can see the real-time value, which is being updated on the screen, as well as the online, offline attribute. If I go to my web page, you can then see by energizing input number 7, each one of my quantities from the meter is being updated in primary units, and I'm updating my screen as though I was standing in front of the meter. This is an example and a usage of both user-derived function block diagram, and the repetitive use of that derived instruction in ladder diagram. Hopefully, it will cut down on programming time. This is similar to the subroutine function in the -99 Math and Logic, or Advanced Math and Logic, or the -83 Math and Logic applications, which were previously in the Orion. Since we're coming back to the end of our seminar, one of the languages which is perhaps misunderstood is the ability to perform sequential tasks. For example, if in distribution automation sequences, an automation sequence or switchover sequence is usually a step-by-step process. One would wish to perform programming that is more of a visual method. Sequential function chart allows you to do that. Within my programming environment, I'll go into SFC. I've created a program, which is a simple SFC program. An SFC program allows me to create a visual diagram, and since we are online, this visual diagram says the initial step when entering the program is the block with a double line around it. Within the programming environment, I can write various scripts in ladder diagram, function block diagram, instruction list, which will execute either when an initialization and entering the block occurs, on the rising edge of program entry, continuously every time the step is in that stage, or whenever the execution of that step transitions from one step to another. The SFC structured function chart, or sequential function chart, has two types of instructions. A block instruction, which is a step, and a transition step, or a transition, which is indicated by this horizontal line with a number beneath it. In this application, if I look at my transition, Whenever input 1 from my simulator goes to a value of 1, I will transition from my initial step to my second step. Additionally, in my transition step, I will perform an action. So on my simulator, I hit input number 1, and my logic will transition to step number 2, and I can see on my simulator output number 1 is energized. Going to my programming environment and going to my transition step number 2, I see that there is logic on my entry into the step. I am going to be energizing DCIO output number 1. If I go to my watch list, if I go to my outputs, I can watch the status of my outputs, that when I transition through the blocks, I will, in this case, upon step number 2, whenever input number 2 goes true, I will transition from step 302 to step 303. Additionally, within this step, I can see that I'm counting the executions in instruction list every time this logic is executed. So I'm increasing this counter every scan, showing you that the logic programmed in this end block will execute with every scan that is included within step 302. If I transition my input number 2, you will see in a matter of seconds that I will transition from step 302. Everything in step 302 will have stopped executing. I'll go to step 303. Additionally, on my web page screen, output number 2 will energize and illuminate. Therefore, continuing, my SPI list, each one of my variables is updated, and I can also see by my other steps, I have parallel steps. In this case, if input number 3 goes high, I will transition to step 304. But since this is a parallel step, both step 304 and 401, which turned on my output number 2, will transition accordingly. Finally, when I transition out of this step by depressing input number 4 from my logic, when input number 4 goes true, I will then transition out of the step, and the remaining steps have no logic in them, and they will transition once input number 5 goes high to step 301, which is the beginning of my reset or my sequence. Based upon this, as you can see, the IEC logic can be rather helpful in automating and visualizing sequential processes such as DA automation. Since I'm able to perform jump statements, I'm able to time each one of the steps, and it's more of a visual programming package. Since we're near the end of our seminar, and we have had limited time, I hope that this brief introduction to IEC 61131-3 has been helpful to you in visualizing the capabilities and opportunities to apply this, matching the skill sets of your organization. If you think that the IEC 1131-3 logic is impressive, wait till you see the 61850 logic, which will be demonstrated at DistribuTech in San Diego 2013. I hope this demonstration has shown you the interoperability with our Orion applications and traditional applications. The IEC 1131-3 is an application which is field upgradable at a minimal cost. It's completely integrated with tool sets of our traditional NCD programming package, giving you the advantage of not having to install additional packages whenever you transition to the -101 IEC 1131 option. I'd like to thank each of you for your participation in today's webinar, but if you do have additional questions, please feel free to contact me. I've given my contact information, email information, and I look forward to discussing this application with each and any one of you, or if you would wish to have this application sent to you with these slides, I am more than happy to do that